Hello, this is video 79. We're going to be talking about periodic motion. This is the first video in our new units for simple harmonic motion. Before we can talk about simple harmonic motion, we just want to describe a few quantities that describe periodic motion. So periodic motion is simply motion that repeats. This little girl is just swinging up and down. That motion repeats. Is periodic. We describe periodic motion with a period and a frequency. In this video, we're going to be discussing period and frequency as well as amplitude, which would have to do with how high does she bounce up and down. Let's start by talking about period. Period is the time it takes for an object to complete one complete cycle of its motion. And we use the symbol T for the period. So if we look at this clock here, what is a complete cycle of its motion? Complete cycle is a complete back and forth. So if this clock here were to start on the leftmost side over here, and it went all the way to the right, and then it went all the way back to the left, that would be one complete cycle. So the time that it took to go back and forth would be the period. In the case of a clock, you know that it makes a ding on each side every second, so you know that to go from left to right takes 1 second, and then to go back to the left side takes another second. So that means that the period for this clock would be 2 seconds. So you can see that we use the SI unit of the second to describe period. Let's do an example for period. A mass oscillates on a horizontal spring with period T equals 2 seconds. If the mass is pulled to the right and then released, how long will it take for the mass to reach the leftmost point of its motion? So you've got to visualize the motion here. If this mass is pulled to the right and then it oscillates, well, when it oscillates, it's going to go back to its equilibrium position here. Right, it's starting from the rightmost point here. It's going to go to the left through the equilibrium, and it's going to keep going until it compresses the spring as much as possible. Once it has reached this point, which is the leftmost point of its motion, then it's going to go back to the right. So we're asked in this question here, how long does it take to go from the rightmost point here all the way to the leftmost point? So if we can figure out what part of a cycle this is, how much of a cycle this is, we can relate it to the period. So a complete cycle for this mass would be to go all the way to the left and then to go back to the right. So I can't draw it here because the video is in the way, but you can see that just going to the left is going to be half of a cycle. So just going to the left is going to be half of a period. So if the period is 2 seconds, that's the time to go back and forth. Just to go to one side is just going to take half of that time, which is 1 second. Now let's talk about the next variable, which is the frequency. And we use this variable to describe periodic motion. Frequency is the number of complete cycles or vibrations per second. So how many cycles go by every second? Over here we have a graph showing the heartbeat of someone, and you can see that every time it beats there's the spike here. So a complete cycle is given by from one peak to another. So the time that it takes to go from one peak to another will be the time for a complete cycle, which would be the period that we just discussed. So in this case, the period would be 1 second, because you can see there's 1 second in between each cycle. Now the frequency asks us how many cycles do we have each second. So if you just look at a time interval of 1 second here, for example from 0.5 to 1.5 seconds, you can see there's only one complete cycle. So for this particular picture here, the frequency is 1 cycle per second. The unit of cycle per second is called the hertz. So that's the SI unit that we're going to use. Now I do have an equation here that says that the frequency equals 1 over period. So you may be wondering, well, where does that come from? Because in this particular picture, the period was 1 second and the frequency was 1 hertz. But we can best understand this equation relating the frequency and the period if we just draw another diagram. And I'm going to draw the motion of an object that is periodic, and it's going to resemble a cosine wave in this case. But just picture this as showing the motion of an object as a function of time. So this motion, this object is just going up and down, up and down. So it's periodic, it's repeating itself. So let's say that when the object gets here, that this takes 0.5 seconds. The time here is in seconds. And let's say that by the time it completes another cycle over here, that 1 second has elapsed. So 1 complete cycle is from here to here. The time for 1 complete cycle is the period. You can see from this graph that the period is 0.5 seconds. Now what is the frequency for this graph? The frequency is the number of cycles per second. Can you see that there are 2 cycles? There's 1 cycle here and then another cycle here. There are 2 complete cycles per second. You see we've gotten to 1 second here. So the frequency is 2 hertz, 2 cycles per second, while the period was 0.5 seconds. So you can see that there is an inverse relation between period and frequency. If you do 1 divided by 0.5, you do get 2. So let's do a question for frequency. A mass oscillates on a horizontal spring with period t equals 2 seconds. What is the frequency? So all we have to do here is use the equation that frequency is 1 over period and plug the numbers in, and we're going to get 0.5 hertz. So all this means is that if a complete cycle takes 2 seconds, then that means that every second you're only going to have half of a cycle. So that shows you the relationship between period and frequency. Let's talk about one more variable that's going to describe periodic motion, and this is the amplitude. The amplitude is the object's maximum displacement from equilibrium. So I have another picture of a spring oscillating up and down, and the first picture here shows the equilibrium position, and then it's going up where the spring is compressed to its maximum. Then it goes all the way back down until this point right here where it is stretched to the maximum. So the displacement from equilibrium, you draw a line going through the center of this motion, and you can see that the maximum displacement is at the peak here, or over here, that's the peak. So that is what we call the amplitude A. So just draw a line through the center of the motion and find the distance to the crest or the trough of that motion. The symbol for the amplitude is A, and it is going to be measured in meters because we're talking about a displacement from equilibrium. Let's do one question for amplitude to finish up this video. A mass oscillates on a spring with amplitude A, just like in the previous picture. What is the total distance traveled by the mass after 1 period of oscillation? It is best to do this question by looking back at the picture. So after 1 period, what is the distance traveled? So first of all, the period is a time for 1 oscillation. So if your oscillation is starting here, a complete cycle goes up and down all the way up to here. The complete cycle is from this point on the left to this point on the right. So how far does the object travel? You might think, oh, 2a, right? Because there's an a here and there's an a down here. But you really have to think about the motion. The mass is going up to here. That's traveling a distance a. Once it's here, it goes back to the equilibrium. Well, can you see how that's another distance a traveled down here? And then it goes down all the way to the bottom point here. That's another a. And then it goes back up to go back to the equilibrium position. That's another a. So it actually turns out that in one complete cycle, after one period, it travels a distance of 4a. So this question was just to get you familiar with that definition of amplitude, that distance from the center to the max or the min. And we also talked in this video about period and frequency, and we'll see these again in the next few videos.